effect means the phenomena of emission of electrons from a metal surface when electromagnetic radiations of sufficiently high frequency are incident on it. It is called photoelectric effect. Okay. So what do you mean by photoelectric effect? The phenomena of emission of electrons from a metal surface when electromagnetic radiations of sufficiently high frequency are incident on it is called photoelectric effect. The photolight generated electrons are called photoelectrons. So the generated electrons we call it as photoelectrons. So escaped electrons we call it as photoelectrons. Understood? So photoelectric effect means the phenomena of emission of electrons from a metal surface when electromagnetic radiations like light radiations, UV rays, infrared, etc. are sufficiently high frequency incident on the metal surface. That type of electron emission we call it as photoelectric effect. Okay. For example, alkali metals like lithium, sodium, potassium, cesium show photoelectric effect with visible light. Okay. While the other metals like zinc, cadmium, magnesium respond to ultraviolet light. Okay. The next one is experimental study of photoelectric effect.
Okay. Solar panel can be used to produce electricity, and its working is based on the photoelectric effect. Let's learn about this through an experiment. Using the apparatus shown, let us study the experiment that explains the photoelectric effect. The apparatus consists of an evacuated glass or quartz tube T with a transparent quartz window W that permits radiation to pass through it. S is a source of monochromatic radiation. The evacuated tube consists of a photosensitive metal plate C, called the emitter plate or the cathode plate. This is similar to the functioning of the solar cells in a solar panel. The emitter plate C can be made of photosensitive metals like magnesium, zinc, and cadmium. These metals produce the photoelectric effect with ultraviolet radiation. However, if the source of light used is visible light, then the photoelectric effect is observed with metals like lithium, sodium, potassium, cesium, and rubidium. Another metal plate A, called the collector plate or the anode plate, is also sealed inside the evacuated tube. A battery B is connected to the emitter and collector plate to provide the potential difference through a commutator K, which is used to reverse the polarity of the cathode and the anode. The apparatus also consists of a rheostat RH, which can be used to adjust the potential difference applied between cathode and anode, and a microammeter A, which measures the photoelectric current in the external circuit. The emitter plate is now maintained at negative polarity, and the collector at positive polarity using the commutator, so that the electrons emitted by the cathode can be collected by the collector or anode A. Monochromatic radiation from source S passes through the quartz window W and is incident on the photosensitive emitter plate C. The photosensitive emitter plate C starts emitting electrons. The potential difference between the cathode and the anode accelerates the electrons towards the collector plate, and hence this potential difference is now referred to as accelerating potential. the emitted electrons reach the collector, and when they flow in the external circuit, the resultant current, called the photoelectric current, is measured by the microammeter A. Using this experimental arrangement, let us now study the variation of photoelectric current when we vary the intensity of radiation, frequency of radiation, the applied potential difference between the plates, and the material of the emitter. Intensity of radiation is defined as the amount of energy incident on a unit area in a unit time. As you increase the intensity of light incident on the metal plate, you will notice that the resulting photoelectric current increases proportionally. This is because, as the intensity of light increases, the number of photons incident per second on the metal plate increases. This results in the number of emitted electrons increasing and hence increases the photoelectric current. Let us now study the effect of the applied potential difference on the photoelectric current. As you gradually increase the accelerating potential across the emitter and collector plates, you will notice that the current in the microammeter increases. We know that this happens due to an increase in the number of electrons that reach the collector plate per second. As the accelerating potential across the emitter and collector plates increases further, you will notice that the current in the microammeter reaches its maximum and remains constant. This maximum value of the current is called saturation current. Saturation current is a consequence of all the photoelectrons emitted by emitter plate C reaching the collector plate A. Now the polarity of the cathode and the anode are reversed. This potential builds a positive charge on the emitter plate that attracts the emitted electrons. The negative charge on the collector plate repels the emitted electrons. Hence, this potential is called retarding potential. As the retarding potential increases, you will observe a sharp decrease in the photoelectric current. This decrease in the photoelectric current is attributed to the decreasing number of electrons that reach the collector plate. As you continue to increase the retarding potential at a particular voltage minus V0 applied to the anode, you will notice that the photoelectric current becomes zero. The minimum negative potential V0 applied to the anode for which the photoelectric current becomes zero is called the stopping potential or cut-off potential. The photoelectric current becomes zero when the retarding potential is strong enough to repel the photoelectrons with the maximum kinetic energy. The maximum kinetic energy of the photoelectrons is equal to eV0. For higher intensities of radiation with the same frequency, the saturation current increases. This reinforces the fact that the number of photoelectrons emitted increases with the intensity of the incident frequency. However, the stopping potential remains the same for all intensities of incident radiation of the same frequency. This proves that for a given frequency of incident radiation, stopping potential is independent of its intensity. Let us now study the effect of frequency of radiation on photoelectric current and on stopping potential simultaneously. When radiation of increasing frequencies of the same intensity is incident on the emitter, then the number of photons incident per second is the same, and hence the number of electrons emitted per second will also be the same. Therefore, the saturation current is observed to be the same, though the stopping potentials V0 were observed to increase. As the frequency of radiation increases, V0 increases. This implies that the maximum kinetic energy of the ejected electrons also increases. According to the relation E V0 for maximum kinetic energy for photoelectrons. But the maximum kinetic energy is independent of the intensity of radiation. It is observed that for copper, ultraviolet radiation can produce the photoelectric effect, but radiation of lower frequencies like green or red does not cause photoelectric emission. This shows that for every metal surface, there exists a certain minimum frequency of radiation called the threshold frequency or cutoff frequency, μ0, lower than which photoelectric emission is not possible, regardless of how high the intensity is. Threshold frequency, μ0, is the minimum frequency of the incident radiation required to just cause photoelectric emission from a metal surface. The threshold frequency is different for different materials of the emitter. This means that although the stopping potential varies in a linear fashion with the frequency of the incident radiation, for a certain minimum frequency, the stopping potential is observed to be zero. This was observed to be true with the case of different materials as emitters. For the same intensity and frequency of light capable of causing the photoelectric effect on different emitters, the photoelectric current remains the same, which proves that photoelectric current is independent of the material of the emitter. Another fact regarding the photoelectric effect is that the maximum time needed for the photosensitive plate C to emit electrons is 10⁻⁹ seconds or even less.